connections don't work at all. Instead, you would have to rewrite the sequence numbers, which requires a more sophisticated firewall that can do packet replacement and stateful packet replacement, because the firewall needs to remember the difference between the sequence number it received and the sequence number it must send out. But even if you can deal with all these, there are still some very low-level effects that need to be dealt with. When packets, things like retransmits in TCP, are sent out on timer interrupts or a fixed time period after a timer interrupt. That means that the clock skew will affect the rate that these are being sent out very slightly. There's going to be some noise, but there's a mathematical operation called the Fourier transform that tries to work out the frequency from a number of samples. And the paper by Yoshi Kono had some promising results from just looking at this. So if you can't hide your clock skew, maybe you can try to make it more constant. You could run the CPU at full load, for example, running SETI at home while doing any of your other work. Firstly, this is inefficient, and it also might not always work. In some cases, it might make things even worse. That's because a CPU, by definition, can only run at a maximum of 100%. But depending on what it's doing, the temperature change will be different. I was able to see this when I compared using Tor to introduce temperature changes and using a program called CPU burn, which is specifically designed to increase the temperature. With Tor, I was getting about a 2-degree temperature difference. With CPU burn, I was getting a 5-degree temperature difference. This means that if you run CPU burn in idle time, when Tor is not running, you're actually making things worse, because the difference between Tor running and CPU burning is 3 degrees, but the difference between nothing and Tor is only 2 degrees. So it has to be done carefully. SETI at home is probably not a good example, or a good way to use this, because it does a lot of floating point operations, and floating point is much more heavy for CPU temperature. More sophisticated devices have something called a temperature compensated crystal. This is an oscillator that's built with a clock crystal and a temperature sensor very near to it. And based on the temperature, it estimates what the skew is and corrects for this. These, in the datasheets, claim to have about a 1 part per million accuracy, which is extremely good. That's a minute every 2 years. But I'm able to detect differences smaller than that. So this might not be enough, but it will depend on how well insulated the PC case is. If you want to go even more upmarket from temperature compensated crystals, very high-end equipment will have oven compensated crystals. These are a clock crystal with a heating element very close to them and a temperature sensor. So they will thermostatically control the heating element in order to keep the temperature more or less constant. And these can get 1 part per billion accuracy. And I haven't been able to measure anything like that so far, but maybe with some improvement in analysis it's still possible. I wouldn't like to say that this is a perfect solution. So in summary, I think temperature covert channels are interesting, and in some cases they're a viable attack in more high integrity systems. In your average system, there's going to be better attacks, but if you've defended against all other avenues, then this might be an adequate way to go. I showed how inducing load on Tor and Cerberus will introduce clock skew, and that can be measured remotely. In the example here, which is from one of the Tor suspected Sybil attack servers, there's quite a lot of noise. This is across the transatlantic, around about 14 hops, but it still allows me to get quite a stable temperature difference out of it. And I showed some other cases where temperature covert channels could be useful. A more higher level point is that even if a system is secure at one abstraction level, it's sometimes helpful to step outside of that, either look more deeply at the hardware or look more at the problem statement and see if that's accurate, because it might turn out that a system that is provably secure in one threat model is actually not secure in reality. So if you want to learn some more information about this topic, yep. The next talk from Roger Dinglendine, the Tor project leader, will describe how Tor works, and another interesting aspect of it is how it can circumvent censorship. Tomorrow, George Zanezis will be talking about traffic analysis, which I have hinted at a few times in the talk, but he'll be able to give you a lot more details. There's the paper on which this was based has got a lot more details on how the experiments were run, and there's a short summary of that in the blog posting, which is linked to from the FAR plan. If you want to know more about the clock skew measurement itself, I couldn't fit that in my paper, but the paper by Yoshi Kono gives a very good explanation of how that works. And these slides and all the source code I've used for doing these measurements is online as of today. The code isn't pretty, but it does work. So if you're interested in these kind of cool things to do on security, or you've got any ideas yourself, consider submitting something to Usenix Security. Deadline's quite soon, so get working, but it's a good conference if you have some time to go there. Oh, and one final thing. We eventually did track down the person running the Tor the Tor suspected Sybil attacks, and it was actually an accident. There was no malicious intent, but it was still interesting to find out. Maybe if someone tries it for real, we'll be able to have some tools for defending against that. So that's all from my talk, but I'm happy to have any questions.
Hello. Hi. How much traffic do you need to send to do these measurements? Are we talking 10,000s of packets or millions of packets, or?
I was sending, let's see, 1 packet every 1.5 seconds for round about a day. So very large number of packets. That's actually not very important, the number of packets being sent. What's much more important is the duration of the attack. I think I could greatly decrease the number of packets being sent and still get largely the same results. Because the reason you send multiple packets is to remove noise. Things like the latency can be removed, or jitter in latency can be removed by multiple packets. But a bigger source of the difficulty is how long it takes for some clock skew to have a significant difference in the graph. And that's for 2 reasons. Firstly, CPUs, or a PC has quite a high specific heat capacity, so pumping some energy in it will make it change very slowly. And also, clock skew is very small, things like 1 part per million, so you have to wait for a very long time before that's up to a few milliseconds. So I think you'd still have to run the attack for many, many hours, but the number of packets sent doesn't have to be all that large.
So effectively, you can still detect clock skew even though network jitter would be in the multiple millisecond range through the numerical analysis you were talking about?
Yes. In all my tests for reasonable networks, the jitter had a fairly stable minimum, and that's all I require. Yoshi Kono did a lot more experiments, and they tested on the Planet Lab network, which is tens of computers, maybe hundreds of computers across the university, and they were able to get this attack to work for around about 1 part per million on every node apart from one in India.
I have another idea for defending against these attacks. Couldn't you just use a sort of fan control temperature sensors in the main board and just keeps the CPU on the same temperature level using these fan speeds, and like slowing down the fan if the temperature drops and speeding it up if the temperature rises.
The important thing to keep it at a stable temperature isn't the CPU, it's the clock crystal. And this is harder to keep at a stable temperature because it's almost physically connected to the case. I haven't tried to optimize this attack, but one of the computers I tried did have a temperature compensated fan, and it was varying in speed, but it still wasn't enough to affect this. Maybe with better temperature compensation and a temperature sensor closer to the clock crystal, that could work. It's very similar to a temperature compensated clock crystal in that case.
Would it be possible to measure your own clock skew and compensate for that using, for instance, NTP?
NTP is deliberately very slow in how it finds out its clock skew. It has something called the time constant, which is over a period of several days. And this is because NTP simultaneously corrects for clock skew and also clock phase. And it will rapidly become unstable if it tries to compensate over a very short period of time. So I haven't shown any graphs here, but when I was looking at an NTP compensated clock, you could still see when temperature changed. It just was noisy, but I think it would be possible to have an algorithm that knows about NTP and is able to detect when it's being corrected. Because in NTP, you see a jump when it alters one of its variables. So NTP probably isn't good enough. Well, also, I should say that not all clocks are compensated against NTP. The one I was doing, the Jiffy counter, isn't compensated against NTP, and that's intentional because the clock doesn't have to be accurate, but it does have to be more or less stable in order to get the right properties from the TCP timestamp.
Excuse me? What if you use the NTP controlled system clock for all the timestamps? It shouldn't be that much of a problem to modify the TCP stack.
That will cause some problems with TCP timestamps, although they might be a bit too subtle, because the timestamps do need to be more or less stable in order to get the right properties, and NTP will occasionally cause jumps. So that's probably why the authors decided to use the Jiffy counter rather than something else. I think in OpenBSD and Windows, there's a very similar result. If you did do it, then you get noise because of NTP, but I think it would be possible to remove that because NTP reacts too slowly compared to the effects that I'm looking at. I expect that there will be some stability problems if you try to correct much faster than what NTP currently does.
What do you use yourself for as a reference when measuring clock skew?
I was just using my own crystal clock. I was taking advantage of the fact that the room that I'm in is quite well insulated. Overnight, it will only change in 1 or 2 degrees, which will cause some errors in my result. If anyone has better clocks, for example, a radio receiver that's hooked directly into the PC can get a very stable clock. And if you can use that for the experiments, then you might be able to get better results.
Would it be possible to use GPS receivers or network time clocks from DVB RCS or similar two-way satellite communication systems as a reference instead of using NTP or local temperature-controlled oscillator, and improve clock accuracy using those kind of network or radio-based clock?
They have avoided a lot of the problems of NTP. The reason NTP can become unstable is because it also has to take into account of network latency. Things like GPS or MSF don't have those problems. you still have the problem of how do you apply this compensation at a sufficiently low level that it's not going to have externally measurable devices. So if you can feed it directly into the clock crystal before it goes into the interrupt controller, then that will probably work. If you start doing software control, then that will affect some clocks, but not all of them. And looking at the Fourier transform of the packet emission timer might still be able to identify that.